video, we're going to extend what we've learned about the trigonometric functions and the 6 associated ratios to encompass situations that involve angles other than acute angles. So we defined our 6 trigonometric ratios based on the sides of a right triangle, the 2 legs and the hypotenuse. And what we know, among other things, about a right triangle is that in addition to the right angle, the other 2 angles have to be acute angles. So far, if we're talking about a trigonometric ratio applied or in terms of a particular angle, that angle can only be an acute angle. If we're going to talk about a function, though, ideally we want functions to be able to handle as many different inputs as possible. We want the domain of the function to be as large as possible. And we know, of course, that there are more angles than those that just range from 0 degrees to 90 degrees. So what we're going to talk about in this video is how we would extend the concepts we've already looked at to deal with other angles other than acute angles. In order to deal with other angles other than ones that we would get just by drawing a right triangle, we're going to put our right triangle into the coordinate plane. So what we know about the 6 trigonometric ratios, all of that is going to be consistent with what we're going to do here. But the fundamental thing that's going to change is the fact that now our side lengths potentially will not all be positive numbers. So based on where we put our triangle in the coordinate plane, we're now using coordinates to represent our side lengths. So specifically, the leg lengths of our triangle will be related to the xy coordinates, and the hypotenuse of our triangle we're going to relate to the diagonal distance from the origin, and we're going to call that distance r, and we'll see why that's going to be a little bit later. So imagine taking your right triangle, here's your right angle, here's your 2 acute angles. We're going to focus on this particular angle as the angle in question, the one we're evaluating our trig ratios for. And imagine taking that triangle and putting this angle at the origin and then drawing the angle with that angle oriented in standard position. So we defined standard position before. It means the vertex of our angle is there at the origin, and we're opening onto the positive x-axis. So if we were to place our right triangle in the coordinate plane, we go from the following labeling, which was adjacent, opposite, and hypotenuse, to this particular labeling. We could call this x, we can call this y, based on the fact that we end our angle at an ordered pair that we can call xy, and then rather than labeling this diagonal as the hypotenuse, we're going to call this r, and r is going to be defined as the distance from the origin to this particular point. Other than that, all the ratios are still the same, but what changes is the fact that now if we were to take this angle and rotate around to maybe the second quadrant or the third quadrant or the fourth quadrant, we could still draw a right triangle, but potentially at that point the x and y coordinates may no longer have negative, they may no longer have positive values, they may have negative values. So the ratios will be defined in the same way, but based on the quadrant that our right triangle ends up being drawn in, we're going to potentially have different values for the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent. But the benefit here is that we're no longer going to be restricted to just angles there in the first quadrant, just acute angles. Acute angles are going to take us from 0 degrees to 90 degrees. Well, now we're going to be able to look at angles in any quadrant, which is going to broaden a lot of the possibilities for how we can use trigonometric functions. So again, because we're now in the coordinate plane, we have to consider the possibility of negative trigonometric values. So let's go through the coordinate plane, and based on how we've defined our trigonometric ratios, let's analyze what's going to happen for each of our trigonometric ratios just based on the quadrant that our angle is in. So one thing we need to be sure about, the angle we define is always going to be incident with the origin. It's always going to be the angle that intersects there at the origin. So the original angle that we look at, if we're just talking about a right triangle, the original theta we think about is going to be theta in standard position. So that's going to be our theta. And so we have our initial side along the positive x-axis. We have our terminal side somewhere out in the first quadrant, and that's going to take us to an ordered pair xy. What we want to focus on, though, is what are the signs going to be for the coordinates at this particular point in space. Well, if this point is in the first quadrant, we know that the x-coordinate is going to be positive and the y-coordinate is going to be positive. And if we think of that in terms of how we labeled the sides of our right triangle, that means the adjacent side is going to be positive and the opposite side is going to be positive as well. Now, by definition, the length of the hypotenuse is always going to be a positive number. The reason it's always going to be positive, is because we define it as distance. This particular length is defined as the distance from the origin to this particular point in space. And distance, by definition, is always a positive number. So the only thing that can change signs potentially are going to be the coordinates that take us to this particular point in space. But in this case, if we were to draw our triangle in this particular quadrant, the x-coordinate is positive, the y-coordinate is positive, the hypotenuse, or this diagonal distance, is positive. So all of the side lengths of our right triangle are all going to be positive. Well, if all the side lengths are going to be positive, then any trig ratio we take is going to be a ratio of two positive numbers. So if we're talking about an angle in the first quadrant, we're only looking at positive trigonometric values. So all the functions are going to have positive values if we have an angle that's there in the first quadrant. And again, that shouldn't necessarily be surprising, because if we're talking about angles in the first quadrant, we're talking about acute angles, we're talking about angles that exist within a right triangle, so it shouldn't be surprising what we're seeing in that case. Now, what if we were to draw a corresponding right triangle here in the second quadrant? So we can think of this as our theta. We can think of this acute angle as our theta, but really, theta is that angle. If we really want to think about what theta is in that case, if we've gone all the way from standard position, all the way over here, theta is actually, in this case, an obtuse angle. It's some angle that's bigger than 90 degrees. In order to use trigonometric ratios, though, we have to think of the right triangle that would exist based on this being an acute angle. We're going to talk about what this angle is. This angle has a specific name. The actual value for theta is an obtuse angle, but we have this associated angle right here that's going to be an acute angle, and that angle is going to allow us to label our sides of our right triangle. So what happens if our terminal side ends up in the second quadrant? Well, specifically, what's going to happen with the coordinates at that particular location? Well, we know if our terminal side and its associated point is in the second quadrant, the x-coordinate is going to be negative and the y-coordinate is going to be positive. So that means this side is going to have a negative length, this side is going to have a positive length, and again, the diagonal distance from the origin to that particular point along the terminal side is always going to have a positive value. So because one of the side lengths now has a negative value, this is going to change the values for some of our trigonometric functions. So which ones are going to be affected? Well, let's analyze, just based on our ratios, what's going to happen for this particular angle. So suppose this is our angle, the one that's incident with the origin. Well, sine is defined as our opposite over our hypotenuse. So opposite over hypotenuse will be positive or positive, so it'll still be positive. So our sine is going to have a positive value. Now cosine is adjacent over hypotenuse, in which case we're taking a negative over a positive. The division of a negative by a positive results in a negative. So the cosine is actually going to have a negative value if our triangle ends up in the second quadrant. What about the tangent? Well, tangent is going to be opposite over adjacent, so positive over negative which is also going to be negative. So tangent will also be negative. Now, if we know what happens for these three functions, the same things are going to happen for their reciprocals, because all that's going to change is the order in which we divide a positive and a negative. So if sine has a positive value, then its reciprocal, cosecant, will also have a positive value. If cosine and tangent have negative values, then their reciprocals, secant and cotangent, will also have negative values. Now, what if we were to continue around and our angle were to end up in the third quadrant, something between 180 degrees and 270 degrees? So again, what's the actual angle? The actual angle in question is the angle that takes us all the way from the positive x-axis to this terminal side over here. But in terms of drawing a right triangle, this is going to be the angle we use in order to draw our right triangle and define our trigonometric ratios. So we can draw our line to the x-axis. Notice it's always going to be drawn to the x-axis regardless of where we are. So the right angle is going to exist there on the x-axis. So what happens if our terminal side is there in the third quadrant? Specifically, what are the signs of the coordinates going to be? Well, our x is going to be negative, but in this case, our y is going to be negative as well. So we have a negative x, we have a negative y, so the only thing that's positive is going to be the length of the hypotenuse, if we want to think about it that way, our distance from the origin to this particular point. So what's going to happen to our ratios in this quadrant? Well, what about the sine? Sine's going to be opposite over hypotenuse, which is going to be a negative over a positive, which will be a negative result. So sine will be negative. Cosine is adjacent over hypotenuse, which will be a negative over a positive, which will also end up being negative. And then tangent is going to be opposite over adjacent, which is negative over negative. Well, dividing a negative by another negative results in a positive output. So tangent will be positive in that quadrant. And again, the reciprocal functions for these three are also going to have the same signs. So if tangent is positive, cotangent will be as well. If sine and cosine are negative, then cosecant and secant will be as well. And then our last quadrant, our fourth quadrant, again, imagine drawing that vertical line, and then there's our right angle. The actual angle we're analyzing is going to be the angle that takes us all the way from the positive x-axis around to this terminal side. So it's going to be an angle between 270 and 360 degrees. But the angle we're using to draw our triangle, define our ratios, is going to be this acute angle that we make between the terminal side and then the x-axis. So what do we know about the coordinates here? Well, x is positive, but y is negative. And then again, we know that our length, our distance from the origin to this particular point in space, always going to be positive. So what do we know about our ratios in this case? Well, sine is going to be opposite over hypotenuse, so negative over positive, which is going to be negative. So our sine is going to have a negative value. Cosine is adjacent over hypotenuse, so positive over positive, which will be positive. And then tangent is going to be opposite over adjacent, so negative over positive, which is going to be negative. The reciprocal functions behave the same way, so if cosine is positive, secant will be positive. If sine and tangent are negative, then cosecant and cotangent are going to be negative as well. And it's a good exercise to go through just to analyze what's going to happen quadrant by quadrant. But at the end of the day, as long as you know those ratios and you can draw the triangle in the correct quadrant, you don't have to memorize the signs of what's going to happen for each of our trigonometric ratios. As long as you know the quadrant you're in and you can draw the right triangle and label it correctly, all you have to do is take the ratios of those side lengths and the signs are going to take care of themselves. But what we're going to notice are some patterns for where specific functions are positive and where those specific functions are negative. And we're going to use those to draw some specific conclusions about all of these different trig functions, particularly sine, cosine, and tangent. So let's look at a couple examples, finding some actual trigonometric values when we're not just looking at a right triangle, when we have something that exists within the coordinate plane. So for our first example, we're going to let the ordered pair -2, -5 be a point on the terminal side of our angle that's drawn in standard position. And we want to find the values of our 6 trigonometric functions for theta. So our ordered pair, -2, -5, is on the terminal side. In other words, the diagonal that we draw from the origin to the terminal side of our angle. That's going to be a point on that particular side. So the coordinates -2, -5 tell us that we're going to have a point in the third quadrant. So this is going to be in quadrant 3. So we'll say this is -1, -2, and then -1, 2, 3, 4, 5. So that means we're going to have an ordered pair right there. And this is going to be the terminal side of our angle. So this will be the actual angle, theta. That's the actual angle, theta. So notice it's going to be an angle somewhere between 180 and 270 degrees. But the angle we're going to use to analyze what's happening with this triangle that we actually draw in this quadrant, that's going to be the angle we use. So in order to get the full right triangle, I'm going to draw a line onto the x-axis, and that now becomes my right angle. So my ordered pair here, again, this is -2, -5, which means this side length is -2, this side length is -5. Now we know in order to find our trigonometric ratios, we need all 3 side lengths. So we still need to know what's the length of the hypotenuse in this right triangle that we've drawn in the third quadrant. And this again is where the Pythagorean theorem is going to be helpful. So this is going to be our adjacent side, this is our opposite side, or more generally, they're just the legs of a right triangle. So based on the Pythagorean theorem, we know that -2 squared plus -5 squared is equal to this diagonal distance, which we're now calling r squared. And again, we'll come back to why this is called r at a later time. So -2 squared is going to be +4. Keep in mind, you square a negative. Squaring any number gives you a positive output. -5 squared is going to give you 25, and that's going to be equal to r squared. So that means r squared is equal to 29, which means r is equal to the positive or negative square root of 29. Now, is it going to be positive? Is it going to be negative? Here we're talking about positives versus negatives. The signs can change. But because this is representing a distance, the distance from the origin to this particular point, distance is always defined as being positive. So we want the positive square root of 29. And also, it's worth noting, root 29 cannot be simplified any further. If it could be, of course, we would want to simplify that further. So once we have our triangle drawn, we have all of our sides labeled, we have enough to find the values of all of these trigonometric ratios. So the sine of our angle, specifically the sine of our actual theta, but using ratios defined from this acute angle and this associated right triangle. The sine is going to be our opposite, which is -5, over our hypotenuse, which is root 25, or root 29, excuse me. So -5 over root 29. Now we know we need to rationalize. In general, we're always going to rationalize unless told otherwise. So rationalizing that, that's going to be -5 root 29 over 29. Now if we take the cosecant, that's going to be the reciprocal of our sine, and we could just take the reciprocal of this non-rationalized version, knowing that its reciprocal will be rationalized. So that's going to be negative root 29 over 5. Notice the signs are going to be the same. So if our sine function was negative, our cosecant function will also be negative as well. Now what about the cosine? Well, that's going to be adjacent over hypotenuse. So negative 2 over root 29. And again, we need to rationalize. So negative 2 root 29 divided by 29. Okay, and then the secant will be the reciprocal of that. So we can take the reciprocal of the non-rational version, and that's going to be negative root 29 over 2. And then our tangent is defined as our opposite over our adjacent. So negative 5 over negative 2. Notice that double negative. Those are going to cancel when you divide. So opposite over adjacent is going to be 5 over 2. And then cotangent is the reciprocal of that, which is 2 over 5. So do all of these signs for all of these functions match up with what we thought would happen, just generically speaking? So we determined that the sine was negative, the cosine was negative, the tangent was positive, and then the cosecant was negative, the secant was negative, and the cotangent was positive. Does that match up with what we just assumed, predicted would happen on the first page? Well, based on being in the third quadrant, tangent and cotangent were positive, and then sine, cosine, cosecant, and secant were all negative down in this quadrant, and that's exactly what happened. And again, it has nothing to do with the actual values for our coordinates. It has to do with the fact that their location makes them negative. Being in the third quadrant will make my x and y negative, and so the associated ratios we get from our right triangle will also result in associated positive and negative values. So if we're given a point, essentially this is the same thing as being given the legs of a triangle. We're just being given it in a different form. So being given x and y, that's essentially the same thing as just being told the legs of a right triangle. We draw the triangle in the coordinate plane, we label everything else, and then we go from there. Now we can also be given information in other ways. So what if we're given a trigonometric value, given information about a function, and maybe some additional information to help us determine what quadrant we're in? So here we've been told that sine is negative 4 over 7, and we've been told that the cosine of the same angle is a positive number. Based on that, we want to find the values of our other trigonometric functions. Now we could flip back over and we could use that information to determine what quadrant we're in, but let's see if we can just figure it out based on what we know about sine and what we know about cosine. Well, sine, remember sine is defined as our opposite over our hypotenuse. Okay, now we've been told that the sine is negative. Okay, so that means when we take this ratio, it resulted in a negative output. Now what we know about being in the coordinate plane is what we're defining as the hypotenuse is always going to be a positive number. So whatever this ratio is, we know the hypotenuse was a positive number. Well, if we took the ratio of two numbers and it came out negative, but we know the denominator of that ratio had to be positive, then we know the numerator has to be negative. So the opposite side has to be negative, and the hypotenuse has to be positive. Well, hypotenuse being positive, that's going to be the same for all four quadrants. But if the opposite side is negative, that does give us information about the quadrant. So the opposite side from the origin, the opposite side is always defined as our y. It's the side we get from the y coordinate. Well, here we're saying the opposite side, the y coordinate, is going to be negative. So that means we're either in the third quadrant, where the y coordinate would be negative, or we're in the fourth quadrant, where the y coordinate would be negative. So what that means also is that if we hadn't been given this piece of information, we would be in one of two quadrants and we wouldn't actually know enough to determine which one we were in. So what we were also told then is that cosine, the cosine of theta, is greater than 0. Well, let's think about what that means. Cosine is defined as adjacent over hypotenuse. And we've been told that this is a positive number, that this ratio is positive. Now again, the hypotenuse, we know that has to be positive. Since it's defined as distance, distance is always positive. If this ratio is supposed to be greater than 0, it's supposed to be a positive number, then that means it has to result from the division of two positive numbers. So what do we know? We know that the opposite has to be negative and the adjacent has to be positive. So the opposite side, again, that's your y. The opposite side has to be negative, which means we're in one of these two quadrants. But the adjacent side, which is going to be your x, the adjacent side has to be positive, which means the adjacent side is along the positive x-axis. So our x is positive based on this, our x is greater than 0, and then based on this, our y is less than 0. That uniquely defines a quadrant. X is greater than 0, y is less than 0, which means our angle is an angle in the fourth quadrant, something between 270 and 360 degrees. And that's going to give us all the information we need to both draw our triangle and then label it from the actual ratio we were given. So here's the terminal side for our angle. It doesn't have to be to scale, it just has to be in the right quadrant. We go out to this particular point, and then there we go, we can draw our right triangle. So this is our actual angle, theta. But in order to draw our triangle and analyze our ratios, this is going to be the angle that we're using, that associated acute angle. So based on that being our angle and this being the value for sine, let's label what we know. So we know sine is going to be opposite over hypotenuse. Our opposite has to have the negative sign because we know the hypotenuse can't. So the opposite is going to have to be negative 4. This is going to be negative 4. And the hypotenuse is going to have to be positive 7. So this means we now have to determine the value of the adjacent side, otherwise known as our x-coordinate. So using our Pythagorean theorem, x is what we're solving for. So x squared plus y squared, which is negative 4 squared, is equal to 7 squared. It's worth saying, be very careful when you set up the Pythagorean theorem. Your leg lengths, in this case your x and your y, have to be on one side of the relationship and your hypotenuse is on the other side. So be very careful how you set that relationship up. So that means x squared plus 16 is equal to 49. So x squared is equal to 49 minus 16, which is going to be 33. And so if we take the square root, we get x is equal to the positive or the negative square root of 33. Well, 33 is not divisible by any perfect squares, so we know that's fully simplified. So is it positive or is it negative? Well, that is going to be determined based on the quadrant we're in. We know our terminal side for our angle is in the fourth quadrant, which means x is positive and y is negative. We were solving for x, so that means it's going to have to be the positive square root of 33. If we had been in another quadrant, perhaps we'd been in this quadrant where x was negative, then we would have kept the negative version of this value. Okay, now that our triangle is labeled, we can label all of our other ratios. Now cosecant, we didn't actually need the triangle to label cosecant because we know what sine is, and we know that sine and cosecant are reciprocals. So if the sine is negative 4 over 7, cosecant is negative 7 over 4. Again, same sign, just the reciprocal. Now cosine is defined as our adjacent over our hypotenuse, which is going to be root 33 over 7. Root 33 over 7. And then secant is going to be the reciprocal of that, so 7 over root 33. And if we rationalize that, it's going to be 7 root 33 over 33. 7 and 33 don't have any common factors, so that's fully simplified. And then our tangent is going to be our opposite over our adjacent, so negative 4 over root 33. And if we rationalize that, that's going to be negative 4 root 33 over 33. And then our cotangent is adjacent over opposite, which will already be rationalized, so negative root 33 over 4. So again, let's double check. Did we end up with the same signs that we expected to end up with? So we determined that sine, cosecant, tangent, and cotangent were all negative, and then cosine and secant were both positive. Does that match up with what we anticipated? Well, sine, cosecant, tangent, and cotangent all negative, and then cosine and secant were both positive. So it does match up with what we anticipated. Let's do one more example like that. Finding the quadrant is typically the most challenging thing we have to do when we're drawing these triangles. So let's do another example where we have trig information and we need to actually find the quadrant from that. So here we've been given the tangent, and again we've also been given information about the cosine. We've been told in this case the cosine is negative. So we're going to have to use those ratios again, the idea of the side lengths, what they represent in terms of coordinates, and then go from there. So let's start with the tangent. Okay, so we know that tangent is defined as opposite over adjacent. So we have the opposite over the adjacent. And so we know that the result is negative. When we divide the opposite by the adjacent, the result is negative. Now, because either opposite or adjacent could be negative, we can't definitively say this one's negative and this is positive, or this is positive and this is negative. We can't definitively say that yet. What we can say though is that if we divide these two numbers and the result is negative, the two numbers have to have different signs. We can make that determination. So either it's negative over positive, or it's positive over negative. So what that means is that we're in one of two quadrants, one of the two where the x and y coordinates have different signs. So that means we're either in the second quadrant or we're in the fourth quadrant, one of those two. In the first and third, the opposite and adjacent would have the same sign. So when we divide them, the result would be a positive number. So we're either in quadrant 2 or we're in quadrant 4. Now what about the cosine? We know that the cosine is less than 0. So adjacent over hypotenuse is going to be a negative number. It's going to be less than 0. Well, we know hypotenuse has to be positive. Remember, that's always defined as a positive distance. So if the result comes out negative, then that means the adjacent side has to be negative. Well, if the adjacent side is negative, that means the adjacent side, remember that's our x, that means we're over here. If the adjacent side is negative, that means our x is negative. Well, that also gives us information about this ratio, right? So if the adjacent has to be negative, we know our denominator over here has to be negative. And if the result from division was negative, then in order to get that from a negative denominator, we know our numerator had to be positive. So our adjacent is negative, our opposite is positive. If our opposite is positive, remember that means y. So we have a positive opposite side, which means y is greater than 0. So we're in the quadrant where x is less than 0 and where y is greater than 0. So x is less than 0 and then y is greater than 0, which means we're in the second quadrant. So here is our point. Again, don't worry about it being to scale. It just needs to be in the right quadrant, and we need to be able to label things correctly. So here's the terminal side of our angle. Here is the line we can draw to draw our right triangle. So this is going to be our angle, theta. And this is going to be the associated acute angle we use to draw our triangle and define our ratios. So tangent is our opposite over adjacent, and we know the opposite is positive and the adjacent is negative. So the opposite has to be a positive 20 and the adjacent has to be a negative 21. Okay, now we need to know the length of our hypotenuse. So we know that x squared, which is negative 21 squared, plus y squared, which is 20 squared, is equal to r squared, where r's are unknown. So let me do this one. Let's see, negative 21 squared. Now make sure when you type this in, if you're going to type this in, you have to put parentheses around a negative when you square it. Otherwise you will get a negative output and And you know that squaring a negative results in a positive, so make sure you put parentheses around it. That's going to give us 441, okay, plus 20 squared, which I know is 400. That's going to be equal to r squared. Add these two together, which tells us that r squared is going to be equal to 841. And if I'm not mistaken, surprisingly enough, that is actually a perfect square, and sure enough, it is. So that means r is going to be the positive or negative square root of 841, which is equal to positive or negative 29. So believe it or not, we actually had pretty good numbers here. Now, is it positive? Is it negative? Again, we're solving for r in this case. R is defined as a distance, which means it has to be positive. So that is going to be positive 29. Now, because none of these side lengths involve a radical, rationalization will not be necessary here. All of our answers will be rational to begin with. So our sine, our opposite over hypotenuse, is going to be 20 over 29. Our cosecant is the reciprocal of that, so 29 over 20. Cosine is the adjacent over the hypotenuse, so negative 21 over 29. Now, we were told that cosine should be negative, and that also checks out from the triangle and from the ratio. Secant is the reciprocal of that, so 29 over 21 negative. Negative 29 over 21. And then take the reciprocal of tangent to get cotangent, so negative 21 over 20. And there we go. There are our values. Okay, so we've looked at a few different situations where we can be given information in a variety of ways that will allow us to draw a triangle specifically in one of the 4 quadrants of the coordinate plane, and then label a triangle from there and define everything using our trigonometric ratios. Now, notice what we've used in all these situations, though, in order to find our values for our particular angle theta, which in this case happened to be an obtuse angle. It was between 90 degrees and 180, not something that actually exists within a right triangle. In order to define what we needed for this angle theta, we used this associated acute angle, the one that happens to be incident with the x-axis. That was the angle we used to actually draw our right triangle. And as it turns out, we did that in the other 2 problems as well. So for the first one, we had an angle that was in the 3rd quadrant. The 3rd quadrant is going to take us to an angle between 180 and 270, which can't even exist in a triangle at all. All the angles in a triangle have to add up to 180 degrees, so we can't have an angle between 180 and 270. So even though we can't draw a triangle for this angle, again, we used this acute angle closely associated with this one in order to draw a triangle and label things and find our ratios. And then same kind of thing over here. Our angle was in the 4th quadrant, so we used this acute angle to draw a triangle, label, and find our ratios. So this acute angle that we keep finding for all of these other quadrants, this angle has a special name. It's what we call a reference angle. So it's the angle we reference in order to determine what we need about non-acute angles. Every time we draw this angle, it is an acute angle. It looks a little bit different depending upon the quadrant we're in, but it's always going to be an acute angle. So this particular reference angle, which we're going to label as theta prime, so if our non-acute angle we're interested in is what we're calling theta, theta prime is our reference angle. That's going to relate our given angle, the one we actually want to find trig values for, to one of the angles in the 1st quadrant. Well, what do we know about the 1st quadrant? Well, we know any actual real right triangle could be drawn in the 1st quadrant, which also means that all of the coordinates in the 1st quadrant are going to be negative. Our x-coordinate is negative, our y-coordinate is negative, and of course our distance r is also defined as being negative. What that also means is that all of the trigonometric values for angles in the 1st quadrant are going to be positive numbers. Every ratio results in a positive outcome. So when we used this particular acute angle, for instance, this acute angle right here, it allowed us to draw our triangle and then find our ratios. So even though this angle is actually an angle that exists, technically speaking, within the first quadrant, once we drew this angle in the correct quadrant and then just labeled our coordinates correctly, one was positive, one was negative, that took care of all the signs for the trig ratios for us. So knowing what this angle is, knowing that it's an acute angle, if we were to find the actual trig values for this angle we've drawn, all of its trig values would actually be positive because this particular angle is a first quadrant angle. But the fact that we drew it in the second quadrant is why we ended up with some negative values. So we use this angle, what we now call the reference angle, to find all the values for theta with the assumption that because theta is in this particular quadrant, we're going to have to adjust the signs. We have to know that the x-coordinate is negative and the y-coordinate is positive. So we're going to use these reference angles because they're in the first quadrant, because they represent actual angles that could exist within a triangle. The angle that we want to find values for and the reference angle we're using, they're going to have all of the same trig values. All of the ratios will be the same except for differences in sign, not the sine function, but SIGN, in other words, positive or negative. So if we know everything we need to know about the first quadrant, about actual right triangles, actual acute angles, and then the triangles that result from those, then all we have to do to determine information about the second, the third, and the fourth quadrant is make the appropriate adjustments for sine. So this particular right triangle, for instance, if we had drawn that right triangle in the first quadrant, same shape, just in the first quadrant, all of the coordinates would have been the same, except everything would have been positive. This would have been a positive 21, a positive 20, and then of course still a positive 29. Once we took that triangle and moved it, the only thing that changed is the fact that one of the side lengths became negative just based on the quadrant we were in. So if we know everything we need to know about this acute angle, the resulting triangle for the first quadrant, then we know everything we need to know about that triangle in general. If we move it to this quadrant, we adjust a sign appropriately. If we were to move it down into the third quadrant, the x and y would both be negative, but otherwise the values would be the same. If we move it to the fourth quadrant, again, this would be positive, this would be negative, and we would just adjust the signs accordingly. So if we can learn everything we can, everything we need to know about the first quadrant, about those acute angles, about those standard right triangles, then we actually know everything we need to know about any quadrant. As long as we understand this idea of how we would move the triangle to a different quadrant, how we would draw it in the different quadrant, and what the signs are in that particular quadrant. Now, as we look at these particular triangles, these particular angles, and specific trigonometric functions for specific angles, we need to keep in mind, what do the trigonometric values relate to in terms of the coordinates? Well, let's go back to that diagram on the first page, and I want to specifically think about sine, cosine, and tangent. What are the patterns we're seeing for sine, cosine, and tangent? Well, here in the first quadrant, let's think about sine first. Here in the first quadrant, sine is positive. In the second, sine is positive. In the third and fourth, sine is negative. So what coordinate is really related to sine in this case? In terms of if the sine changes sine, well, what associated coordinate changed sine as well? Well, if we're in the first and second quadrant, where the sine is positive in both cases, notice those are the quadrants where the y values are going to be positive. If we're in the third and fourth quadrant, where the sine values are negative, well, those are the quadrants where y is going to be negative. So if y is positive, the sine function is positive. If y is negative, the sine function is negative. So the deciding factor on the sine, SIGN, we choose for the sine function is going to be whatever happens with the y coordinate. So sine directly relates to y. In other words, if we know what the sine, SIGN, is going to be for y, then we know what to expect for the sine trigonometric function. Now what about cosine? Same idea. What's happening with the cosine as we travel throughout the coordinate plane? Well, in the first quadrant, it's positive. In the fourth quadrant, it's positive. And then in the second and third quadrants, it's going to be negative. Well, what coordinate seems to be associated with that? Well, in the first and fourth quadrant, what is consistently positive? In those two quadrants, the x coordinate is positive. In the second and third quadrant, the x coordinate is negative, and the associated cosine value is negative. So in the first and fourth, where x is positive, cosine is positive. In the second and third, where x is negative, the cosine is negative. So x is going to be the indicating coordinate for cosine. Now what about tangent? Tangent is a little bit different. So tangent is positive in the first quadrant, and it's positive in the third quadrant. And then in the second and fourth, it's going to be negative. Here the relationship is the fact that the signs are the same versus the signs being different. Think about how we defined tangent. We defined it as the adjacent, or excuse me, the opposite over the adjacent. Whenever they have the same sign, SIGN, we know that the ratio for tangent is going to be positive. Whenever they have different signs, we know the ratio for tangent is going to be negative. So in order to determine what the sign is going to be for tangent, it's going to be dependent on both x and y. Are they the same or are they different? So tangent is going to be related to y over x. And as we've determined in the first three examples that we did, the reciprocal functions behave the same way. So sine, whatever we know about sine, we also know about cosecant. Whatever we know about cosine, we also know about secant. Whatever we know about tangent, we also know about cotangent. There we go. So if we can determine what we need about the first quadrant, and we can determine what we need to know about the signs of the coordinates, then we can take all this information from the first quadrant and we can extend it to the second, the third, and the fourth quadrant with this idea that this triangle that we draw in the first quadrant, we can draw it in the second, the third, the fourth, just adjusting the signs of our coordinates. But we're going to use reference angles in order to draw this triangle that moves around the different quadrants. The angle we use to draw that triangle and the angle we use to evaluate our trigonometric functions, that is our reference angle. So determining the reference angle is going to be important. Once we can determine the reference angle, that's going to tell us what are we looking at in the first quadrant as our point of reference. If we know this about this angle in the first quadrant, well, what does that angle look like if we move it to the second quadrant, the third, or the fourth? What do we know about the signs in that quadrant? That's going to give us all the information we need to find all of our trigonometric values regardless of the angle we're looking at. So conceptually speaking, a reference angle is found by taking the shortest amount of rotation from our terminal side of our angle to the x-axis. So we've actually seen all three different situations where we need a reference angle. So in this particular example, notice our angle was in the second quadrant. The shortest amount of rotation to take us from our terminal side to the x-axis was this angle right here. So that would be defined as our reference angle. For the previous two, this one we had an angle in the third quadrant. So the shortest distance from our terminal side to the x-axis was this right here. That was our angle right there. That was the amount of rotation. And then for this one, we had an angle that was in the fourth quadrant. If our terminal side is here, then our reference angle, the shortest amount of rotation to the x-axis, was that angle right there. And of course, if we're in the first quadrant, we don't need a reference angle at all. The angle we already have is already acute. So we have to keep in mind that if we're finding the shortest amount of rotation to take us from our actual angle to the x-axis, this can happen in the positive direction We can rotate in the positive direction. Remember, that means we're going counterclockwise. Or we could rotate in the negative direction, which means we're going clockwise. So what are we looking at with a 3 we've already seen? Well, if this is our reference angle, notice the angle was determined by continuing to rotate in the positive direction. So if this was our actual angle, the reference angle would be an angle that's rotated in the positive direction from this angle, this terminal side, down to 180 degrees, down to the negative x-axis. What about the other two? Well, for this one, if this is our reference angle and this is our actual angle, then the reference angle would be found by rotating backwards from the terminal side to the negative x-axis. And then for this last one, if our terminal side was there in the fourth quadrant, the reference angle would also be a positive angle that we find by rotating however much more we need to get from our terminal side to the positive x-axis back from 0 to 360. So the reference angle is going to look the same in pretty much every case, but it can result from positive rotation, it can result from negative rotation. At the end of the day, we're always going to define it as an acute angle, something between 0 and 90 degrees. But how we actually find it, what it actually looks like on that coordinate plane based on our actual angle, that's going to differ depending on the quadrant we're in. Now, the other thing we're going to have to keep in mind is we're doing our best to generalize trigonometry for any angle, which includes things beyond that standard rotation from 0 to 360 degrees. What if we kept rotating in the positive direction past 360? Or what if we rotated backwards in the negative direction? So we had a negative angle, something rotated away from 0 degrees, negative 30, negative 60, something like that. So if our angle is beyond the interval from 0 degrees to 360 degrees, or beyond the interval from 0 to 2 pi radians, then first thing we have to do before we can come up with this idea of a reference angle, determine what it would be, draw our triangle, all of that, first thing we have to do is find a coterminal angle. So we talked about how we'd find coterminal angles. Remember, that's going to be the angle within the standard rotation, within this actual interval, that is related to the angle we have. So we want to find the angle within that interval that looks the same as the actual angle we're looking at. So we're going to do a bunch of examples using reference angles. There's going to be a lot of layers to evaluating a trigonometric function based on a particular angle. Number one, is it within the rotation we want? Is it within that standard rotation? Number two, based on whether or not it is, what's our reference angle going to be? How do we use the reference angle? How do we adjust our signs? What do we do there? There's going to be a lot of layers here. So we're just going to do a bunch of examples using these reference angles, and we'll go from there. So how do we define the actual reference angles? Sometimes we can just define them by looking at them. It's just going to be an inspection kind of thing. But it's a good idea to formalize what we're looking at before we get too much into just looking at something and trying to figure something out. So as before, let's determine what everything looks like in the 4 different quadrants. Specifically, if we draw a right triangle in one of the 4 quadrants, well, what does the reference angle look like in order to draw that right triangle? If we're in the first quadrant, this is going to be our triangle, which means the reference angle is the actual angle in the triangle. So not only is this our value for theta, but if we were going to call it a reference angle, the shortest distance from our terminal side to the x-axis, that's also going to be our reference angle. So here in the first quadrant, this reference angle is our actual value for theta. What that actually means, though, is that if we're in the first quadrant, if we're looking at angles in the first quadrant, reference angles aren't very meaningful. We don't really need them. And again, let's go back and look at the signs again. So if we're here in this quadrant, our x is positive, our y is positive, and always our r is positive. So we have 2 positive coordinates. All of the trig values are positive over here. Now, what if we rotate around to the second quadrant? Well, here we know that our x is negative, but our y is positive. And if we want to draw a right triangle, here's our right triangle, here's our right angle. This would be our actual angle, since this is our terminal side rotating from 0 degrees over here. This is our terminal side, but this is our reference angle, this particular angle. It's the angle we get if we go from this terminal side down to the x-axis, which means we're continuing to rotate in the positive direction. So our x is negative, our y is positive, and again our r is going to be positive, and we've discussed what's going to happen with our trigonometric functions over here. Well, if this is our actual angle, I'm going to label it for this one. If this is our actual angle right here, how do we find the reference angle in relation to this? In terms of degrees or in terms of radians? How do we determine what the reference angle is going to be? Well, it's the amount of rotation that it's going to take to get from our actual angle to the halfway point, to 180 degrees or pi radians, depending on the angle measure we're in. So it's the difference between that measure, the halfway point, and the amount of rotation we already have that takes us to our actual angle. So that term difference, that means subtraction. It's the difference between a halfway rotation and the amount of rotation we already have. So in degrees, that's going to be defined as 180 degrees, that halfway rotation reaching the x-axis, which is what we want. It's the difference between that and the amount of rotation we already have, represented by theta. And then our corresponding radian measure, 180 degrees, remember that's the same thing as pi radians if we convert units. So in radians, that would be pi minus theta. So if we know what theta is, and we know it's in the second quadrant, our reference angle is going to be found using one of these formulas if we want to get back to formulas. Now what if we continue rotating and now we're in the third quadrant? Well, here we know both the x and the y are negative. So here's our angle, or here's our triangle here. So x is negative, y is negative. Again, r is still positive. This will be our reference angle. But again, if we think of it as the shortest rotation from our terminal side to the x-axis, then it's rotated in the negative direction. So here it's how far would we have to rotate backwards to get from our angle, which is greater than 180 degrees, greater than pi radians, back to 180 degrees, back to pi radians. So it's still going to be subtraction, but we're going to take the larger angle and subtract that half rotation. It's the difference between the two. So our angle, greater than 180, minus the actual half rotation to 180 to pi, it's the difference between the two. So it's going to be theta minus 180 degrees if we're talking about degrees, or it's going to be theta minus pi if we're in radians. And then our last quadrant, if we're in the fourth quadrant, we have a positive x coordinate, a negative y. Here is our vertical. There's our right angle. And our reference angle is going to be right here. So the actual angle rotates all the way from 0 around to this terminal side. But our reference angle, the shortest amount of rotation from our terminal side to the x-axis, is going to be this angle right here. Now this is rotated in the positive direction. It's the amount we would need to continue rotating to get back to where we started, back to 360, or if we're talking about radians, back to 2 pi. So in this case, it's the difference between that full rotation and the amount of rotation we already have, which again takes us to this fourth quadrant angle. So again, difference means subtraction. Full rotation minus the amount of rotation we already have is going to give us the difference between the two. So in degrees, that's going to be 360 degrees minus our fourth degree angle, theta. Fourth quadrant, excuse me. Or in radians, it's going to be 2 pi minus theta. So we can use the formulas. You certainly can use them if you need. Try not to rely on memorizing formulas though. We are going to get to the point where we do have to memorize some. These are not ones that are worth your time to memorize. It's going to be a better idea to just draw a picture, because once you have a picture of what the situation looks like, finding the reference angle usually is a little bit more straightforward, and we can just visualize what we're looking at. Now, one other thing I want to point out, a common mistake that a lot of students make when they're talking about finding a reference angle. I want you to notice that each of these reference angles and their associated formulas are related to the x-axis and the x-axis only. So for the second quadrant, we're relating to 180 to pi. Same thing for the third, 180 and pi. And then for the fourth quadrant, we're relating to 360 and 2 pi. I want you to notice that none of these formulas relate at all to the y-axis, or to 90 degrees or 270 degrees if you want to think of it that way. That's because when we draw the right triangle is always drawn with respect to the x-axis. Our angle is always incident with the origin along the x-axis, and so we don't ever do anything with 90 or with 270 or pi over 2 or 3 pi over 2 if we want to talk about radians. So all of these formulas are going to relate to measures along the x-axis. So if you feel tempted to do something with the y-axis, remind yourself we're not using the y-axis, we're using the x-axis exclusively. That's how we draw our triangle, and that's how we find our reference angles with respect to the x-axis. So let's look at some examples. Let's see how we find reference angles, how we use them, so on and so forth. Okay, so we want to evaluate this function using reference angles. So we want to find the sine, the value of the sine, for the radian measure for pi over 3. What we want to do first is draw a picture. What does 4 pi over 3 actually look like? Specifically, what quadrant is it in? We don't have to be to scale, but we need to know specifically what quadrant are we in. Well, before we make that determination, it's going to be important to know, are we within the first rotation? Is 4 pi over 3 between 0 and 2 pi? Remember, the way we looked at this is to think of 4/3 as the coefficient for pi. We're looking at angles between 0 pi and 2 pi. Those are the angles we want to use with respect to reference angles. So is 4/3 pi between 0 pi and 2 pi? Well, we can officially make that determination by determining what 4/3 is. 4/3 is 1/3, or 1 1/3 pi. So it is between 0 pi and 2 pi. That means it is within our first rotation. Well, where is it? What quadrant is it in? That's again when we have to think about what our axis measures are. So here we're at 0 pi. This would be 1/2 pi. This would be 1 pi. This would be 3/2 pi. And then we make it all the way back around to 2 pi in that one rotation. So we're at 1 1/3 pi. So we're between 1 pi and 1 1/2 pi. We're somewhere down here. So I'm going to draw that particular angle. We know our angle in question is in the third quadrant, which also means if we were going to draw a triangle, that's going to be our triangle, and this angle is going to be our reference angle. If we want to use ratios, if we want to find a reference angle, that is going to be our reference angle. Well, what is that angle? What is that acute angle that takes our larger angle and rotates it back to the x-axis, in this case the negative side of the x-axis? Well, it's going to be the difference between how far we've rotated and that half rotation that we want to reach, which is at pi radians. So our reference angle is going to be defined as our angle, which in this case is 4 pi over 3, minus that halfway rotation to pi. It's the difference between the two, so minus pi. Okay, and if we get our common denominator, that's going to be 4 pi over 3 minus 3 pi over 3. which comes out to just pi over 3. So in other words, pi over 3 is the first quadrant angle that we're going to reference in order to determine everything we need about this angle 4 pi over 3. So the sine of 4 pi over 3 is going to be the same as the sine of pi over 3, except for differences in sine SIGN. Now, what do we know about this quadrant? We know that our x is negative and our y is negative. We also know that sine is related to our opposite side, to our y. So if sine is related to this side, we know that it's going to be negative. So if we put all of that together, what that tells us is that the sine of 4 pi over 3 is going to have the same value as the sine of pi over 3. It's going to look the same in terms of drawing a triangle. If we were to draw this triangle in the first quadrant, find all the ratios based on the first quadrant, 4 pi over 3 and pi over 3 are going to have the same ratios, except that we have to make the adjustment for the consideration that our triangle is now drawn in this third quadrant. So the sine of 4 pi over 3 is going to be the same thing as the sine of pi over 3. Well, what is the sine of pi over 3? We could technically plug that into the calculator, but the drawback of doing that is we're only going to get an approximation. So for now, you're just going to use this chart. I've given you this chart. We're going to reference the chart, and that's going to give us our trigonometric values, sine, cosine, and tangent, specifically for the special values at 30, 45, and 60, otherwise known as pi over 6, pi over 4, and pi over 3. Why do these values come out the way they do? We'll talk about that in the next video. Why do they come out the way they do? There's a reason for that, and we'll look at that later. So sine of 4 pi over 3 and sine of pi over 3 are going to be the same, except for possible adjustments in positive versus negative. So let's write out that relationship. So sine of 4 pi over 3 is equal to the sine of pi over 3. I'm going to leave some space. Because pi over 3 is the reference angle for 4 pi over 3, the same triangle would be drawn for each of these angles. They have the same trig values, so the actual value is going to be the same, except that we have to adjust potentially a sign. So everything in the first quadrant has a positive value, so this, whatever this number is, this is a positive number. What is this number going to be in terms of its sign, though? If we're in the third quadrant, we know the sine, which is related to our y coordinate. Sine is going to be negative. So these two are going to have the same absolute value, but we're going to have to make this number negative in order to account for the fact that this is in quadrant 3. Well, what is the sine of pi over 3? Well, we're going to use the chart for now to make that determination. So when our angle is pi over 3, its sine is going to be the value square root of 3 over 2. So that means the sine of 4 pi over 3 is negative, whatever that is. So it's going to be negative square root of 3 over 2. That is going to be the sine of 4 pi over 3. Now, how can you use your calculator? You can use your calculator to check that. Let's see what negative root 3 over 2 is. So negative square root of 3, arrow out, and then we're dividing by 2. Okay, so negative root 3 over 2, that's the value. What is the sine of 4 pi over 3? Is it the same thing? Well, if we're going to plug in sine of 4 pi over 3, this is a radian measure. We need to make sure that our calculator is in radian mode, so verify that. If it's not, remember you need to change it from degrees to radians. So we are in radians. So let's take the sine of 4 pi over 3 radians. And sure enough, it's the same value. So we're not going to report that as the value because that's just an approximation. We want negative root 3 over 2 since that's the exact value, but that at least is a verification that our number makes sense and that our numbers match up. Now let's do another example. Okay, cosine of 570 degrees. So now we're back in degrees. We know if we want to use the calculator, we're going to have to convert to degree mode. First off, this angle, 570 degrees, is it within the first rotation? The answer here is no. It's not between 0 and 360 degrees. So first thing we need to do is we need to find the angle within that rotation that's going to be coterminal to 570, the angle that looks the same. If it looks the same, then it behaves the same way. Coterminal angles will have all of the same values because they look the same. If you drew a triangle, the triangle would be the same, and so on and so forth. So 570 degrees, let's find a coterminal angle to that. So 570 degrees, now we want to go backwards, so we're going to subtract 360. So 570 minus 360 is going to give us 210 degrees. Now that is between 0 and 360, so that's the value we want to use. Now what quadrant is that in? Well, here's 0 to 90 degrees, 90 to 180 degrees, 180 to 270, so that means we're somewhere in the third quadrant. So again, we're down here. So I'm going to draw my angle. So our actual angle, technically 570 is rotate once and then rotate again. 210 is just the portion that rotates from 0 to the terminal side. But because 570 and 210 look the same, their initial and terminal sides are the same, we can use 210 in place of 570, knowing that all the trigonometric values will be the same. So let's draw our right triangle. There's our triangle, which means this is going to be our reference angle. So it's the angle that takes us from 210 back to the x-axis, in this case the negative x-axis represented by 180 degrees. So that means that our reference angle is going to be the difference between how far we've fully rotated and the half rotation at 180 degrees. So 210 degrees minus 180 degrees is going to be 30 degrees. That's our reference angle. So what we know about 570 and 210, all the same values, they look the same. What we know about 210, or what we want to determine about it, we will determine using 30 degrees as our reference angle. So these two angles are going to have all the same trigonometric values except for possible differences in sine. So 30 degrees, which is in the first quadrant, all of its trigonometric values are positive. 210, hence 570, are in the third quadrant, where things are negative, where our x is negative and where our y is negative. So if we were to relate all three of these angles, the cosine of 570 degrees is the exact same as the cosine of 210, because again, they are coterminal, they look the same, they have the same initial and terminal side. This triangle we draw would be the same for 570 as it is for 210. Now we're using 30 to reference the values in order to get the values for 210. So the cosine of 210 is going to be the same as the cosine of 30, except possibly, again, for differences in sign. Do we have to adjust positive and make it negative? That's the question we need to answer. Now 210 degrees is in the third quadrant. We're taking the cosine, which is going to be our adjacent over our hypotenuse. And so adjacent over hypotenuse is going to have a negative value, which means our reference value we will have to make negative in order to accommodate that particular quadrant and the fact that the cosine is going to be negative in that quadrant. Well, what is the cosine of 30 degrees? Again, for now, we're just going to look it up. So when theta is 30 degrees, when we're looking at 30 degrees, the cosine is going to be root 3 over 2. So that means our actual value we want is going to be negative root 3 over 2. So that's going to be the cosine of 570 degrees. Let's verify that as well. So remember, go to your mode. If you've already used radians, you need to go back to degrees. So convert to degree mode. What is the cosine of 570 degrees? Let's see. So the cosine of 570 degrees is negative 0.866, so on and so forth. What we already determined was the value for negative root 3 over 2. It matches up, So that verifies that we found the correct value for cosine. Okay, let's try another one. Also in degrees, but now we have a negative angle, which means it's definitely not within the rotation we want. So negative 225 degrees, we need a coterminal angle to that within the rotation that we want. So negative 225 degrees, add on a rotation to find a positive coterminal angle. So negative 225 plus 360 is going to give us 135 degrees. So that is going to be our coterminal angle. In other words, everything that happens for negative 225, all of its trigonometric values are the same trigonometric values for 135 degrees. Because they're in the same quadrant, we draw the same triangle for them, the ratios would all be the same. So where's 135 degrees? Well, here's 0, here's 90, here's 180. So that means it's somewhere in the second quadrant. So there is our terminal side. Draw our right triangle. Now in this quadrant, this is going to be our reference angle. And we know that our signs are going to be a negative x and then a positive y. Okay, so we want the tangent of negative 225, otherwise known as the tangent of 135. What is our reference angle going to be in order to get the information we need about 135 degrees? Well, we need to find that. So our reference angle is the angle that's going to take us from the rotation we already have to the halfway point at 180 degrees. So it's the difference between 180 degrees and the amount of rotation we already have, which is 135. So our reference angle is going to be 180 degrees minus 135 degrees, which is going to be 45 degrees. So negative 225, 135, they have the same values. 135 and 45 have the same values except for possible differences in sign. So that means that the tangent of negative 225 degrees is going to be the same as the tangent for the coterminal angle, 135 degrees. And that is going to be the same as the tangent for 45 degrees, except possibly for differences in sign. So the tangent of 45 degrees is in the first quadrant. All the trig ratios are positive. What about 135 degrees? 135 degrees is in the second quadrant. Now, tangent is defined as our opposite over our adjacent. So if we were to take a ratio, it's going to be the y-coordinate divided by the x, which is positive divided by negative. Well, positive divided by negative is going to give us a negative. So that means, yes, we will have to adjust the sign again. So what is the tangent of 45 degrees then? Okay, here's our list. Here's 45 degrees. Our tangent has a value of 1. So that means our value for tangent is going to be negative 1. Let's verify that one. So tangent of negative 225 degrees, same as tangent of 135, which is going to be the negative version of the tangent of its reference angle, 45 degrees. So we're already in degree mode, so we're good there. So we're taking the tangent of negative 225 degrees, and sure enough, negative 1. So that checks out. So that's going to give us the fundamental ones that we can check with the buttons. If we want to do other ones, remember we'll just do the reciprocal relationship. So cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. So let's try one of those. And I see a typo already. Let's put in a pi right there. There we go. So that should be cosecant of negative 13 pi over 6. Now this is a negative angle, so it's definitely not within the range of values we want. So we need to find the coterminal angle first. So negative 13 pi over 6. And we're going to add on a rotation in radians that's represented as 2 pi. So that's going to be negative 13 pi over 6 plus common denominator, that'll give us 12 pi over 6. and that's going to take us to negative pi over 6. Now we're not quite there, so let's add on another 12 pi over 6, and that's going to take us to 11 pi over 6. So that's going to be our coterminal angle. So everything we know about negative 13 pi over 6, all the values are the same for 11 pi over 6 because they are coterminal, they look the same. So 11 pi over 6, where's that going to be? Well, this will be similar to the first part we did. Think of this as 0 pi, half pi, 1 pi, 1.5 pi, and then back to 2 pi. So 11 over 6, how many pi's is that? 11 over 6 is about 1.8 pi's. So it's between 1.5 pi's and 2 pi's. It's somewhere in that quadrant, in the fourth quadrant. So I'm going to draw my terminal side, draw my right triangle, which means my reference angle is going to be right here. Okay, now in this quadrant, my x is positive, my y is negative, and what is the actual value of my reference angle? It's the difference between the full rotation all the way back to 2 pi and the amount of rotation that I've already gone to get to my terminal side, which we can think of as 11 pi over 6. So it's the difference between 2 pi and 11 pi over 6. So my reference angle is going to be 2 pi minus 11 pi over 6. We know 2 pi is the same thing as 12 pi over 6. So 12 pi over 6 minus 11 pi over 6 is going to be pi over 6. So pi over 6 is my reference angle for these two angles. So everything we need to know, all the values for pi over 6 are going to be the same as the values for 11 pi over 6 and respectively for negative 13 pi over 6, again except for adjustments potentially in sine. So our cosecant of negative 13 pi over 6 is going to be the same as our cosecant for our reference, or not our reference angle, our coterminal angle. So the cosecant of 11 pi over 6. And just because I'm noticing this now, let me make a note of this. Notice how we put parentheses around this particular angle measure. The reason we did it here and we don't always do it, notice we also had parentheses here, we also didn't have parentheses here. Typically we want to put parentheses around negative angle measures to show that the negative is not a subtraction sign, it's part of the actual angle, it's part of the angle measure. So when we're going to use or not going to use parentheses, if the angle measure is negative, you want to use parentheses. If the angle contains more than one term, if it's maybe one angle plus another, something like that, you want to use parentheses to show that all of that is the input for your trigonometric function. If you're just applying your trig function to a single positive angle, you may not need to put the parentheses. It's really just personal preference at that point. So that's the difference in notation there. Okay, so back to our actual problem. 11 pi over 6, again, coterminal to our actual angle. So these two values are the same because these two angles look the same. And that's going to be the same as our cosecant for our reference angle, which is pi over 6, because this is the angle that forms our right triangle. So what is the cosecant for pi over 6? Well, let's go look at our table. I don't see a cosecant. I do see a pi over 6, so here's pi over 6. We have enough information though. So if pi over 6 is our reference angle and we want cosecant, remember cosecant is going to be the reciprocal of the sine function. So if we know the value for sine at that particular angle, we can take its reciprocal to find the value of cosecant. So the cosecant of pi over 6 is going to be the reciprocal of 1/2, which is going to be 2. Now do we need to adjust the sign? What happens with the cosecant at 11 pi over 6? Well, cosecant and sine are closely related. Sine is going to be related to our opposite. So opposite over hypotenuse is going to be a negative over a positive. So cosecant would be a positive over a negative, which will have a negative sign. So we do need to adjust it. So that means the value of our cosecant is going to be negative reciprocal of 1/2, which is 2. So negative 2. Okay, let's check that one. Now we're back in radians, so let's convert back to radian mode. Okay. Now remember, we don't have a cosecant button. We have to write it as 1 over sine, excuse me. So 1 over sine, and we're taking it for negative 13 pi over 6. And there it is, negative 2. Okay, let's look at just a couple more. We want to do one for each of our trig functions. So now we want a secant of 11 pi over 4. So we're in radians. 11 pi over 4, is that within our standard rotation? Well, again, we want to see, are we between 0 pi's and 2 pi's? How many pi's do we have? We have 11 over 4 pi's, which is too many. We have 2 3/4 of a pi. So we need our coterminal angle that's back within the interval that we want. So we want to go backwards, so we're going to subtract 2 pi. 2 pi can be written as 8 pi over 4. Okay, so we do the subtraction, and that's going to give us 3 pi over 4. That's our coterminal angle. So 11 pi over 4, 3 pi over 4 have all the same trig values because they are coterminal. They have the same initial and terminal side. So 3 pi over 4, that's 3/4 pi. So it's between 1/2 pi and 1 pi. So it's going to be over here in the second quadrant. Here's our triangle. Here's our reference angle. And then in this quadrant, we have a negative x and a positive y. There we go. Okay, what is our reference angle? It's going to be the distance it takes to get from our angle to the halfway rotation at pi. So it's the difference between pi and our angle, or in this case the coterminal angle, which is 3 pi over 4. So 4 pi over 4 minus 3 pi over 4 is going to be just pi over 4. So these two angles have all the same values, and the values for 3 pi over 4 are the same for the values for pi over 4, except again for differences in sign potentially. So the secant of 11 pi over 4 is going to be the same as the secant for 3 pi over 4, since they're coterminal. And they're also going to be the same as the secant for pi over 4, our reference angle, except for the potential adjustment in sign. So secant of pi over 4 is here in the first quadrant, everything is positive. What about 3 pi over 4 and 11 pi over 4, which are in the second quadrant? Secant is going to relate to cosine. Cosine is our adjacent over our hypotenuse. So adjacent is negative, hypotenuse is positive. So negative over positive is going to give us a negative output. So we're going to make it negative. Now every one we've done so far, we have had to make the adjustment. Keep in mind that's not always going to be the case. So suppose, for example, we did a cosecant here. Cosecant is related to opposite over hypotenuse. So hypotenuse over opposite is the reciprocal of sine. That ratio would have still been positive, which means this already positive number, we wouldn't have to do anything to it. You could leave it alone. So not every situation is going to require us to adjust the sign and make our value negative. Just be aware of that. So the secant is going to be the reciprocal of the cosine, and we're looking at pi over 4. So here's pi over 4, here's our cosine. So root 2 over 2 is our value for cosine. So the value for secant is going to be the reciprocal of that. So negative reciprocal, which is going to be 2 over root 2. And now we need to rationalize that. So multiply top and bottom by the square root of 2. So that's going to be negative 2 root 2 over the rationalized radical, which is going to be 2. We now have a common factor. And so the final value will be negative root 2. And that's going to be the value for our secant. So let's check that. Let's see, we are already in radian mode, so that looks good. So don't have a secant button, so we're going to do 1 over cosine. So 1 over cosine of 11 pi over 4. Okay, that's going to be our value. Well, what is the negative square root of 2? Same value. So there's our check. Okay, let's do one final one. We haven't done a cotangent, so let's do a cotangent. So we're back in degrees. We have a negative degree measure, so we know we're going to have to find our coterminal angle by rotating in the positive direction. So negative 960 degrees. Now how many are we going to have to rotate? How many times? Let's see. Let's just do this one on the calculator. So negative 960. If we add 360 one time, that's not going to be enough. What happens if we add another one? Well, it's still not going to be enough, so let's add one additional one. Again, keeping in mind these are representing full rotations in the positive direction, and that's going to take us to 120. So we added on 360 3 times, so plus 3 full rotations of 360 degrees is going to take us to 120 degrees. So that's going to be our coterminal angle. So everything for negative 960 degrees is going to be the same as it is for 120 degrees. All of their trig values are the same. So what quadrant is that going to be in? Well, we're between 90 and 180, so that means we're going to be in the second quadrant. There's our triangle. There's our reference angle. And so if we want the actual value for the reference angle, it's the difference between that half rotation and the 120 degrees that we've already traveled. So 180 degrees minus 120 degrees is going to be 60 degrees. So negative 960 and 120 have the same values, and 60 is the reference angle. So all their values are the same except possibly for adjustments in sign based on the quadrant we're in, where x is negative and y is positive. So the cotangent of negative 960 degrees is going to be equal to the cotangent for 120 degrees, and they're both going to be equal to the cotangent for 60 degrees, except for that potential needed adjustment in sine. So what do we know about cotangent? Well, if tangent is opposite over adjacent, cotangent is adjacent over opposite. So negative over positive, which is going to give us a negative output. So again, we're going to adjust the sign. Now, what is our cotangent of 60 degrees? Here is 60 degrees. Our tangent is going to be the square root of 3, which means the cotangent is its reciprocal, which is going to be 1 over the square root of 3. So that is going to be negative 1 over root 3. We need to rationalize, so that's going to be negative square root of 3 over 3. And then let's check this one last problem. So convert back to degrees if needed. Enter, clear, there we go. So we're taking a cotangent, the reciprocal of tangent. Remember, tangent with that superscript of -1 is not cotangent. We need 1 divided by tangent, and we're applying that to an angle measure of negative 960 degrees, and that's going to be our value. And then we want to verify, is that the same thing as negative square root of 3 divided by 3. Now careful when you type that in. Once you type in the radical and it's radicand, you need to tab out and then divide. Otherwise it's going to put the division inside of the radical, which is not what you want. And there we go. Same value, it matches up. So that gives you a few examples of how you find a reference angle, how you use the reference angle. We're going to use this concept of a reference angle consistently over and over to find all of these trigonometric values. The benefit of using a reference angle is it allows us to relate all of these angles throughout the coordinate plane to the angles in the first quadrant. The angles that could actually exist in a right triangle, What we're then going to talk about in our next video is all of these values in the first quadrant. We just had this table for them. Well, how do we know that these are the actual values? How do we know that the sine of 30 degrees is going to be 1/2 and the cosine is going to be the square root of 3/2? Because if we know these values, if we know everything about 30, 45, and 60, well, that's going to let us deal with 120 since it relates to 60. It's going to let us deal with 11 pi over 4 and 3 pi over 4 since they relate to pi over 4 or 45 degrees. So knowing how to find a reference angle, knowing how to use the reference angle means essentially we have to avoid, or we are allowed to avoid, a lot of memorization, and we can generalize things a little bit more. But why are these trig values what they are? Based on finding a reference angle and using that reference angle. That's what we'll talk about in our next video.